Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrenner, and in this video, I'm going to work 3 examples on AC circuit analysis. Let's do an example. Suppose that the current through an impedance is going to be I of t equal to 3 cosine 377t amps, and that the voltage across that impedance is V of t is equal to 6 cosine 377t plus 90 degrees volts. We want to find the RMS value of I of t, the RMS value of V of t, and the average power dissipated by that impedance. The first thing I want you to notice is that the frequency of the current I of t and V of t are both omega equal to 377 radians per second, which corresponds roughly to 60 hertz. Okay, to calculate the RMS value of the current, 3 cosine 377t, what we need to do is, I usually write I with a little RMS beside it to make it clear. You take the amplitude, which is 3, and divide it by the square root of 2, the unit's amps, and that's the answer. Similarly, to figure out the RMS voltage across that impedance, we take the amplitude, which is 6, divided by the square root of 2, and that's going to be in volts. We went over this in the definition of RMS values. And then what makes this particularly useful is we can calculate the average power, not the instantaneous power, but the average power dissipated by that impedance, and that will be equal to, using the equation P is equal to IV, we have the RMS current times the RMS voltage, which will give us 3 over the square root of 2 times 6 over the square root of 2, which is 18 over 2, which is 9, and the unit is watts. Here's another example. We have a circuit with the input independent voltage source, Vn of t. It's got an inductor, a resistor, and a capacitor. And we can say what happens when Vn of t is equal to 3 cosine 2 pi times 60 t plus 45 degrees volts. I want to know what V out of t is, and we will also go ahead and find what IR of t is, just to show you different values and how to do them. So our first decision is whether or not we want to do nodal analysis or mesh analysis. Either will work, but this looks very nice. It's got a single node here. Of course, here's ground, and of course this node is trivial because it's equal to Vn of t. So I'm going to choose to do nodal analysis. I'm going to call this, well, we could call this voltage V if we wanted, but I want you to notice that this has already got a name. This voltage right here is what's called V out of t as defined, right? This from here to here is V out of t, so from here to here is V out of t. So I will just go ahead and write that in just to remind us that that voltage right there is V out of t, even though it's perhaps obvious. Okay, so let's write our nodal equations. We have V out minus Vn, and I'm dropping the t's here, but we're going to use phasors in just a moment. In fact, maybe we should go ahead and plug in for Vn just to keep our life a bit simple. Okay, so let's just go ahead. What is Vn written as a phasor? Well, it's going to be and I'm going to use capital letters here, although it doesn't much matter for V's. What we're going to do is we use the amplitude, which is going to be 3, and the angle is 45 degrees. So we'll just say 3 at an angle of 45 degrees. Of course, the units is volts. And this would be a good time to go ahead and notice that omega is equal to 2 pi times 60. And of course, the units for omega is radians per second. And now we can go ahead and start writing our equations. And I'll just plug in as I go. Many of you have said that you like that format. So often I will leave it with variables. This time we'll go ahead and plug in values. The current going here is V out minus V in, so that will be V out minus 3 at an angle of 45 degrees over J omega L, so that's J times omega, which is 2 pi times 60, and L is 0.2. So just to recap, this voltage minus this voltage over the impedance, which is J omega L. Okay, then we have this current going down through here. We're not solving for I of R yet, so let's just go ahead and write that as V out over the impedance, which is R, which is 100. So that's the current going down through here. V out minus 0 over 100, and then the current going here will be V out minus 0 over the impedance. V out minus 0, I'll just write as V out. And the impedance is 1 over J omega, which is 2 pi times 60, and C, which is 30 microfarads, 30. I've run out of space. Let me shift it over. Times so 1 over J omega, which is 2 pi 60, and then the capacitance is 30 times 10 to the minus 6, 30 micro. And that will all be equal to 0. Sorry, I've run out of room. Let me shrink this. So now all we need to do is solve. So as I simplify my equations, I'm going to go ahead and leave that pi in there just to keep my answers a little more precise without having to write down a lot of values. So the first thing we're going to do is let's move the Vn part here, right, to the other side of the equation, and then we'll factor out V out as well. We can do that all in one step. We'll get V out times 1 over J times 2 pi times 60 times 0.2. I pre-calculated this. It's going to be J times 24 times pi. And then we have factor out a V out of the second term. We get 1 over 100. And then the third term, what we're going to do is we're going to flip this fraction, and we'll end up with something fairly messy. It'll be J times 3600 times 10 to the minus 6 times pi. And that will be equal to 3 at an angle of 45 degrees, which is the input voltage, right? We move it to the other side, and it's divided by, again, we have J times 24 pi. So let me move this to a clean sheet of paper, or clean screen, however we want to put that, just so I can work on that, because we still have some solving to do. This would be a good time for you to get out your calculator and go ahead and solve for V out, and then come back and check your answer. So as I go along, let's figure out all these parts. The first thing I'm going to do is, using my calculator, or in my case I'm using MATLAB, I go ahead and I compute all these values and write that as, just so you know, the intermediate value will be 0.0100 minus J 0.0020. So that now this is simplified into a complex number. So V out times that number will be equal to 3 at an angle of 40 divided by J times 24 pi. So let me go ahead and write those both as phasors so you can see some of the advantages of that. We have 3 at an angle of 45 degrees, and when we figure out J times 24 times pi, we end up with J times 75.3982, And since we have a J, we know that that means it's at 90 degrees. Now you could put this in your calculator if you want. There's many ways to solve it. At this point, what I normally do is I go ahead and divide 3. You divide the magnitudes, right? You divide 3 by 75.3982. That gives us the new magnitude. And the angle, we'll take 45 and we'll subtract 90 degrees. So that will give us, when I calculate that, I get 0.398 at an angle of minus 45 degrees. And then when I convert this value into phasor notation, what I do is if I have in my calculator or my MATLAB, for MATLAB, I would take this value, I would apply the function ABS, that gives me the magnitude, and the function angle gives me the angle. And so I'll end up with V out is equal to the right-hand side divided by, when we compute this, we end up with 0.0102 at an angle of minus 11.0518 degrees. And you do need to keep a lot of digits here. So be sure and do that. I'm keeping the values in my MATLAB. You should keep them in your calculator. So there's a little bit of, tricks in how to do this. But in any case, I keep as high a resolution as I can in my computation device. And then I would go ahead and do the division. You can just divide the two complex numbers. So this can be a complex number, this is still a complex number, and divide. Or if you prefer, you can divide this number by this number to get the magnitude, which will turn out to be 3.9051. Take minus 45, subtract minus 11, so it's going to give us an angle of minus 33.9482 degrees, and that's V out. The last step is to write it as a time value, so we have V out is equal to 3.9051 cosine, and what was omega? It was 2, and that's one reason I always go ahead and, well, I say always, yep, I did. I always write down omega is 2 pi times 60. I'm just going to leave it as 2 pi times 60 since that's the way it was given in the problem. I could have also given you in the problem 377, which is what's commonly used, even though that's rounding quite a bit. So we have 3.9051 times cosine of 2 pi 60 t plus the angle, which is minus 33.9482 degrees. And of course the unit is volts. So there is the answer to our first question. What is V out of t? The second question we have is what's IR of t? And what I want you to know is, now that we know V out, all we have to do is divide that by R to get IR. So IR of t, and let's go ahead, let me go back for a moment just to be clear and go ahead and put the dependence on t there. So that's a good way to write your answer. IR of t will be equal to V out of t over that 100 ohm resistor. So that will be equal to 0.0391. Okay, or you could have kept a few more digits, but that's enough. Cosine omega, which is 2 pi times 60 t, and the angle was the same, so it's minus 33.9482 degrees. And the angle and the units, of course, is amps. So the complete answer, when I ask for what is V out of t, you want to write it as a cosine. For IR of t, write it as a cosine. And there's the two answers. Okay, here's another example. This one's a little more complicated. we have a circuit with 3 meshes, right? And we have a node here that's Vn, so that's trivial, and we have another node here. So I'm going to go ahead and write nodal analysis equations. So we'll, of course, we know at this node, I've already got it written down, this node is Vn is equal to 10 at an angle of 30 degrees, written in phasor notation. And omega is equal to 1,000 radians per second. I always like to write that down to make me mindful of when I write my final answer. So writing the equations at node that I've labeled V, we have V minus Vn, and Vn, let's go ahead and plug it in. Vn will be 10 at an angle of 30 degrees. So it's V minus Vn over 1 over j omega, which is 1,000, C, which is 1 times 10 to the minus third milli. Okay, so that's this current will be V minus Vn over 1 over j omega times that value C. Then we have a current going through here. That will be V minus 0 over 200, so that was pretty simple. And then the last current here will be V minus 0 over j omega L, so j omega is 1,000, and L is 150 times 10 to the minus 3. And that will all be equal to 0. And so we see we have an equation that allows us to solve for V. Now what we're really looking for is V out. Well, V out is just going to be Vn minus V. So once we find V, we can find Vn. Okay, so all we need to do now is plug in the values and solve. So now we need to go ahead and solve for V. This is fairly messy, but you could do this with your calculator, and I suggest that you do practice that. And so what we're going to do, first of all, is we're going to take the part here and move it to the right-hand side. And when I do the math on that, I end up with 10 at an angle of 30 degrees times j times 1,000 times 1 over 1,000. What's a milli? Will give us 10 at an angle of 120 degrees. Now, you might want to realize at this point that sometimes it's easier to just go ahead and do the division of values, like divide the magnitude and figure out the angle, than it is to plug it into your calculator and use complex numbers. So it's up to you what you feel comfortable with, what's fastest with your tool. Okay, the second thing we do, so then we'll have V times some value, and I go ahead and I plug in I take 1 over this, which is going to be flip the fraction. We end up with j 1,000 times 1 times 10 to the minus third plus 1 over 200 plus 1 over j times 1,000 times 150 times 10 to the minus third. When I do that calculation, I end up with 0.9933 at an angle of 89.7116 degrees. Okay, then we solve by dividing 10 at an angle of 120 by this number, and I end up with 10.0670 at an angle of 30.2884 degrees, and that's of course in volts. Now, one thing I want to remind you to do is go ahead and as you go do some reality checks. When you do that in your calculator, you can do a quick check and see that the value here should be equal to 10 divided by something close to 1. So you know it's going to be about 10. And also the angle is going to be 120 minus something close to 90, so it should be close to 30. Those kind of checks can help you catch careless mistakes pretty quickly. Okay, now the V is not what we were looking for. We were looking for V out. And we notice that V out, let me just put a bar there, V out is equal to Vn minus V, Well, Vn was equal to 10 at an angle of 30. And V is 10.0670 at an angle of, making a little more room for myself here, will be equal to 10 at an angle of 30.2884 degrees, which gives me V out is equal to 0.0839 at an angle of minus 112.8417 degrees. And from that, we can write our answer in the time domain. We would write V out of t is equal to 0.0839 cosine an omega. And what was omega? Omega is 1,000 radians per second. So I have 1,000 t, and the angle is minus 112.8417 degrees, and the units is volts. I hope you found these examples helpful. Thanks for watching.